Welcome, everybody. I'm here today again for a second time with an interview with the distinguished David Sereda from Canada. And for those that saw us last interview, we were chatting and ranting about the enigma of the golden ratio. It's a common interest we have. Today, I have David Sereda here again. He's worked with the Tesla Foundation in the past. He's had connections with NASA. He's planted millions of trees, and he's currently working with Lightstream Harmonics. He's a world expert on frequency and the future sciences, I would say. He's our go-to if we want to know where's all this going to. But before he talks about his connection with NASA, the theme for today is going to be how we square the circle, the mystical association between the square and the circle. And yeah, so David, I was just wondering if you could let us know a little bit about your connection. All my friends are asking me, wow, he worked with NASA. It's sort of a big deal here. If you could clarify your connection there and
Well, NASA is a huge place. I mean, it's not like
Hmm.
it's a very integrated network place. And so I worked for Bogdan Castle-Maglich, who's an MIT particle physicist actually, and he was in the company of some of the most brilliant physicists in the world, like Murray Gell-Mann was around, Glenn Seaborg, who chaired the Atomic Energy Commission under Kennedy, Johnson, Nixon, was around. Murray Gell-Mann, who discovered quarks, and which is a major discovery in quantum mechanics, and Norman Rostocker, who also was a nuclear fusion scientist, was a partner of Magwich's. And so when I worked for him, he appointed me director of the Los Angeles Tesla Foundation. So I was the director of the foundation.
Right.
Magwitch is from the former Yugoslavia, who got his PhD at MIT in nuclear physics and was a professor of physics at Rutgers University, developed a nuclear fusion machine about a cubic meter could power a whole city with a billion watts of continuous non-radioactive nuclear energy.
Amazing.
And when I was working for Magwitch, I did all the communication for two technologies, the nuclear fusion drive Migma, and also his landmine and bomb detection. And for the nuclear fusion drive, I dealt with the NASA head of all propulsion power and energy.
Mm,
And his name is Earl Van Landingham, who was a physicist at NASA. He's passed away.
right.
And I can tell you that I know a lot from Earl about how frustrating NASA is. In fact, you can see with Elon Musk and all these rocket tests how difficult it is
Yes.
to coordinate a rocket to exit the Earth and then safely land as a rocket back on the ground. It's just nearly impossible.
Yes.
And the idea of a nuclear fusion drive, what Earl and I dealt with, I dealt with Earl, so that was my connection to NASA, and Earl became the head of all space access and technology at NASA. So
Fantastic.
he's probably more knowledgeable than any of the heads of NASA are today. But he's passed away.
Right.
And Earl wanted this miniature cubic meter Migma drive that used a beautiful flower of life golden ratio kind of nuclear fusion um, uh, technology
Mm,
to power spacecraft. And Earl told me, I'll never forget my conversations with him, that Magwich's reaction of deuterium and helium-3 in this reactor and the way the reactor was designed could produce propulsion speeds of up to a tenth the speed of light,
mm,
which is
mm,
far beyond the velocities measured of the current UAPs by the US Navy.
mm.
I mean, a tenth the speed of light. So if you take the speed of light at 186, I mean, if you do it in metric, because your country's probably metric,
Yeah.
it's 299, 792 point 458 meters per second times 60 seconds in a minute, times 60 minutes in an hour. So, and divided by 1,000 because those are meters and kilometers. You're looking at 1 million, no, 1 million um, and 70, 1,079, no, 1 billion, no, 1,079,252 kilometers per hour.
Right.
So you divide that by 10, and a tenth the speed of light is 107,000. It's almost 108,000 miles per hour.
Wow, amazing.
So that's what Earl was talking about. Now,
Right.
the UAPs at um, the Navy pilots testifying that they were dropping from above 80,000 feet to the sea level in 0.78 seconds. Like that's just over 60,000, 68,000 miles an hour. Now, so when you look at this, 107,000, 108,000 kilometers an hour, that's what Earl was talking about.
Mm,
This technology that we were working with, trying to get funding for, and we were blocked everywhere. We were blocked by the Clinton Gore administration in Congress. We were blocked by the U.S. nuclear fusion program. Everyone was trying to stop us from attaining this goal. And what Earl wanted for NASA was, he said, we're so tired of these solar panels
yeah.
on the space station. We want real power up here. And these drives are this big. And he said you can control the iris like an opening in the back of the drive to let out more proton streams,
Hmm.
anti-proton streams, to generate this slow acceleration to this incredible velocity.
Right.
And it was all blocked. And
Right.
I was in the middle of it with Magwitch, and I was seeing, why is this blockage going all the way up into Congress? So Magwitch was, if you saw the pattern that the fuel made inside of the Migma drive, it would look a lot like phi and golden ratio spiraling patterns.
Beautiful.
But it's really a tragic story because Magwitch, before he died, can I do a share screen? I think you have
Yeah.
to give me
Yeah. I
permission.
see if we can go with
Uh, Logan,
one participant.
Magwitch.
I'll just click multiple.
Uh,
I've just clicked multiple participants. Yep. So you should be able to share screen.
so there we go. Share. So this is what Migma Fusion looks like on Wikipedia. Let me see if there's any pictures of Magwich's Migma Fusion. He was about to get $50 million from, I want you to see pictures of it. So hang on just a second. Here's Magwitch here.
Yeah. So we got a picture of him. That's
God, nobody even has the Migma principle of controlled fusion. I found an article here. Again, there's no pictures. I'm probably the only one.
Does this mean
Here
this?
we go. Rex.
This is future science. This work has to come out. This work needs to come out. Is this why we're talking about it? It's on our
Well, it needs to come
horizon.
out, but it's also part of phi. You see, here's some diagrams. There's Magwitch when he was young. Here's some diagrams of the orbits of the
Mm,
spiraling vortex where the fusion was going to be created.
yeah.
So Magwitch was very familiar. I mean, he's an incredible mathematician and physicist. So that's my connection to NASA. So I was actually working with joining the fusion project at the highest level of NASA. I wasn't dealing with somebody at the bottom.
That's beautiful. Well, thank you for sharing that. And what I'd like to get to is that because of your amazing background with physicists of the highest order, somehow I believe it's all connected to the ancient knowledge that, say, Leonardo da Vinci had with the Vitruvian Man. But so the theme for today is called the squaring of the circle. So just for those who don't know the Vitruvian Man, I've just got an image here of I would say, besides the Mona Lisa, drawing would be in the mass consciousness. The reason I'm showing this is that everyone's familiar with the Vitruvian Man. So he was like 2,000 years ago. So this inspired Leonardo da Vinci to do this classic drawing. So what I wanted to show about this drawing, I made some notes on the relationship between the square and the circle. I'd just like to read it. The square with its
Mhm.
four corners, like the corners of a house, represents earthly things. So we know that square is form, structure, crystallization, but the circle represents everything that is infinite, perfect, divine, has often been taken to represent the divine or the godly. So the mystical squaring of the circle is a universal symbol of bringing the earthly and the mundane into a proper relationship with the divine. So before I get your thoughts on it, just what I realized about this drawing is that if we were to put our both our arms out like this, and we know that from fingertip to fingertip, as shown in this diagram, from there to there is the same distance as our feet to the head. So that's called the span. So we actually biologically fit inside of a square or a cube. But when the reason why the arms are extended is that when this Vitruvian man forms like the X shape and has the arm out, notice that the fingers are touching the circle and the feet. So so what happens here is that when we extend our arms and legs, we touch the circle. Now, the relationship between the square and the circle is that they are parametrically, the perimeter and the circumference are equal. So today's subject is what's the fascination when we make the square and the circle equal? So I just wanted to uh, start with that. And when you were talking about NASA, David, you said it about that the cube. So when we have a sphere in the cube, the volume of the sphere inside a normal cube, I believe, is 52.3%. And I think that if we move that decimal from 52.3 to the left, we get 0.523, which I believe is the Egyptian cubit. Does that mean there's a sacred proportion in the natural volume of the sphere? So the square and the circle can relate to the cube and the sphere. So is there in your mathematics, is that Egyptian cubit, the 0.523 distance, is that a sacred harmonic in your research?
Well, I can tell you that the this first of all,
Yeah.
let's kind of go in stages there because there's this case of the UAP UFOs that the pilot saw off the coast of the Atlantic that was a sphere with a cube,
Oh.
and they've witnessed hundreds of these. Lieutenant Ryan Graves on the eastern coast in the Atlantic of these cubes within a sphere, and the points of the cube are touching the sphere. And I
Mm.
think everybody missed this. Like, here's a good diagram of what what the pilot saw. You see this?
Right.
It's exactly what Jain is talking about. This is a very famous UAP UFO case
I've never seen this. Never
brought
seen it.
forward by Lieutenant Ryan Graves, the pilot off of, I think it was the Carolinas, off the U.S. Atlantic. They saw these things, and nobody brought up what you just brought up, which
Mm.
is the relationship between the cube and the sphere mathematically, and what's called squaring the circle, or
Mm.
determining the square volume of a circle, which Archimedes, I always like to bring up Archimedes because he's really the father of physics, not Newton. Newton comes much later. But
Mm.
you see how Archimedes does it. Archimedes didn't actually square the circle in the sense of finding the geometric way to construct a square with the same area as a circle. Instead, he established that the area of a circle is equal to the area of a triangle, whose base is the circle's circumference and whose height is its radius. This is very similar what
Mm.
Archimedes does to what I did to square the circle. But
Mhm.
before that, before I get to show you how I squared the circle with phi, I had, because of course the whole idea of squaring a circle is to determine the volume of in square units because we don't have circular units as a unit. We have like a 1 inch cube would be a 1 by 1 by 1. So when you, I mean, just for the audience sake, Jane, just simply, I
Up,
can share my calculator. Just
yeah.
the idea of it, the square volume. So if I have, let's say I have a cube that's 3 inches, and so when you square three, you get 3 times 3 is 9 units, whether that's inches or centimeters. 3 cubed is 27,
Yeah.
right? So to determine the volume of a circle and eventually the volume of a sphere, like a planetoid, is in our mathematics, instead of having a unit called a spherical unit, we do everything in squares, just like Einstein takes the speed of light squared and the speed of light cubed. He doesn't take the speed of light into a circular volume because we don't actually have a circular volume
Mm,
because we convert it to a square. And that's where we get into a lot of trouble
right.
because when I tackled this years ago using a big sheet of square paper,
Yeah.
and the traditional formula is pi r squared. So pi, so let's just use my calculator again, just so people who don't know this can see this before we get deep into this.
Yeah.
If I take a circle whose radius is 37 units. So let's just say it's 37 inches. So I square that and then times pi, my units are going to be 4300.0. So, and this is the decimal. So that would be the square of a circle whose radius is 37 units. That's the way we do it today. Here's the problem is pi is an ever unresolvable expanding formula, as is phi, the golden ratio.
Mm-hmm.
So so a physicist, I've gotten huge arguments with geometers on this subject because people think you square the circle with pi r squared. Yes, that will work for cutting carpet or making a building, but to a physicist who works on the quantum dimensions, it doesn't work.
Right.
And it doesn't work for a lot of reasons. And in fact, doing it on square paper, imagine that all of your lines on square paper. So let's just for the sake of argument, let me just show a sheet of square paper so people can really see what I'm talking about. Square paper. There we go. So let's just look at some squares. Okay, so here we go. Let me just show you what I mean by this. You'll see what the problem is with the whole idea of squaring a circle is that the more refined your unit. So if you draw a circle in here
Mm-hmm.
and you count all the squares, when you get to the edges, you're going to have partial squares because you have a circle going through it,
Exactly.
right?
Yep.
But if you actually do the counting like I did on a really big circle with a big sheet of square paper, pi r squared will drive you crazy
Yeah.
because even though it's not accepted by physicists.
Right.
And that's because guess what? The more numbers of more lines you're using on the paper, all these lines are taking up volume, aren't they?
Exactly. Yeah.
Whereas what Archimedes would do, and when the Archimedes Codex came out years ago and I read it, I love how he does it. He'll determine volume by how much liquid is in this bottle. So his unit is not a square because when you draw a square, your lines and your square are taking up space, but
Yeah.
liquid doesn't. So you'll measure this in milliliters or ounces, etc.
Mm-hmm.
But that's how Archimedes determines, he'll do a mathematical formula. So I could take an irregular form and put it in a tank of water with little lines on the side of my tank measuring the milliliters. And when I drop this in, my tank will rise the volume of this. So
Mm-hmm.
when you're trying to take squaring the circle to squaring the sphere,
Hmm.
which is a real tangible object, you don't have all these lines that you're seeing here.
Can
So
I show,
when you
can
do
I
the square paper method, you
can
get
I
messed
show
up.
a can I show a diagram? I'll just share
Yeah.
the screen, but just for those who don't know the relationship between the squared circle, we can see that this circle that's equal in see there's a difference between area and perimeter, and I'm showing the relationship between the golden ratio. So let me just share the screen to show that better. So share screen. Um, oh.
I'll show you an incredible
So
conundrum
just
here.
show you this one here. So this is what I just showed you now. Just see if it right. So what? Oh no, that's not the diagram. But if you double the radius here, that radius here is 0.636. But if we double that, we get something that's critically important called the square root of the golden ratio. So that's not the diagram, but imagine this diameter of the circle now is 1.272. That's the in Kepler's triangle. That's the height of the Egyptian pyramid. If the base of the triangle is one, let me hold. I'll just let me just get the right one. Or it's over here. I want to show a
Mhm.
difference between area and perimeter. So the one that I'm interested in that uses the golden ratio is the diameter here is 1.272. So that means the radius is 0.636. So if we know that this is the unit square, so the perimeter of the square is 1, 2, 3, 4. So we assume now that the circumference of the circle is also 4. And the only way that that can happen is when the diameter of the circle is the square root of 1.618. We call that the golden root, the square root of phi. So that's this diagram that I was showing here, where the diameter
Mhm.
is phi ratio. So what I'm suggesting is that only the subharmonics of the golden ratio can make heaven and earth equal in a way. Where, so that's why the radius is half of that, which is 0.636. But I want to make it, and we call that traditionally, according to Jean-Michel, who did City of Revelation, he calls that the rectification of the square. So whenever we're saying we're squaring the circle, we're actually talking about the rectification of the square. Now, to go to square area, this diagram on the left, this other diagram, you notice that the corners where the circle goes in, there's a bigger corner here compared to a small corner over here. So this radius here is less than the other one. So so we call that the squaring of the circle. I think if we double 0.563, we get 1.23. I think it's 1.23. Anyway, so I just wanted to make that distinguishment between, are we talking about the parametric squaring of the circle, which is this one, or the square area? And they do different things. A lot of people confuse them all the time. So that's why I just wanted to show that diagram. Um, so then the next level is to think of this as a cube and a sphere. And what's the relationship between a cubic meter and a sphere? What's the corresponding sphere as well? Yeah, so that's someone's done a diagram, and so a friend of mine in America, Joe Dubs, he does this amazing Photoshop. So he's saying that the Vitruvian Man is that if the square here is 1.618, the radius to make them equal, this is to make the perimeters equal, the radius of the circle would be 1. But when I check the calculations, it's off by zero point 0.4 of a meter. It's off by zero point 0.4, which is a big gap. So the diagram that I showed before, where the diameter is the square root of phi, is more accurate. When you work with 1.272, it's more accurate than this is just a generalization. It's close, but it's not accurate. So maybe at this point you might want to come in and talk about, oh, this is the what I was talking about. The key, I reckon, to square the circle is understanding what Plato called the most beautiful triangle. So if this is one and that's the square root of phi, 1.272, Pythagoras' theorem says 1 squared plus root 5 squared gives us phi. So I believe that that's part of the key that the ancients knew how to make heaven and earth equal symbolically. So at this point, you were saying, David, you had an interesting way of measuring the squared circle using the golden ratio. I don't know
Yeah,
about,
I'll show you that.
I'd be very fascinated
Well,
to see
one
that.
thing I did in an Archimedean test, I'm trying to find it in an old email, and I used to have a video that got taken down on squaring the circle. I have a document called Squaring the Circle, but I've lost it. But going from memory, here's what I'm going to do. Because in an Archimedean sense,
Yes,
so let's share screen here. Share let's just share my entire screen. So that's easier. That way so there, squaring the circle. So I'm going to show you two different methods. The traditional method. So if we have a radius of 37 units, let me pull up my calculator. As you'll see the comparison from pi r squared to squaring the circle with the golden ratio of phi. And
right,
you'll see the difference.
right.
And with phi, it's going to be more Archimedean in the sense because I'm gonna absorb all the lines that it takes to make the squares within a square, right?
Mm,
Which is false because they're not really there. They're just theoretically there. And that's why I'm going to demonstrate that pi r squared is wrong. So if I take 37 units and I square it, it gives me 1369 times pi is going to give me this number here. So I'm going to put, and this is using pi r squared. So now I'm going to do it my way.
mm.
This is really amazing. They're
Yeah,
very close, but my way using the golden ratio. Can you see my calculator? I'm not sure
yes,
if you can.
yep, it's good.
Okay. So with 37 units, okay, I got to remember this. Is the radius, so times 2 is the diameter of the circle is 74. So using phi, it is diameter times phi. So watch what happens. So if my diameter is 74 times 1.618,
Yep,
6, 1, I'll just do it. I don't need to do it. I mean, I can do 0.339.887,
yeah, yeah, okay.
but
Let's
it's
be
not
precise. Yeah,
0.339.887. I mean, you can do this infinitely, right?
that's right.
So 74 times 1.61803 is this number here. So watch this. So what we're going to have is 74 now times this number equals, watch what I do now, 119, so times 74 is going to give me this number here.
Right.
Okay. Whoop.
Yep.
What happened? Times 74. There. Okay. Now I'm going to divide that by 2, which is technically half phi.
Right.
Now look at this. Now look at the number above, which is using pi r squared compared to my number.
Mm.
You see, my number has absorbed all the square lines you put inside,
Mm.
which is false.
Yes.
So it's the true volume of the square, which when I expand this formula, I'm going to get
Mm.
the cubic volume of the sphere next. So when I compare the difference, what's the percentage of the difference? I'll tell you what the difference is in percentage. So we just have to go, I'll clear, take this number divided by this number. 97%.
Wow. Yeah.
So, so pi r squared is 97% of my number. Now, that's incredibly close. And when I did this with square paper, you have to understand even if you make those lines razor thin, right? Then see, it's more, this is what I'm trying to get people to see. It's more about the correct volume in
Mm.
a flat circle because you want to go to cubing the sphere next
Yep.
than it is about getting the right number
Right.
that works out in a calculator because you want to know how much space is really there. This is why physicists reject pi r squared, really good physicists. And believe me, this isn't, you have to understand. I mean, I've been in the room with the most brilliant physicists in the world.
Yep.
We're all dead now, and they fight. What they do is they fight.
Mm.
They're like kids and they're nerds and they beat each other up. And it's funny to watch because nobody agrees really. Nobody's at 100% agreement. So
Just
now watch, I'm going to do the same thing. I'm going to do this one more time because I'm going to have my diameter at 74 units, which is 37 times 2, sorry. All right. Times um, the golden ratio. Okay, watch. Times 74. 74 times 1.6180339887 equals this number. To get my, so imagine a circle
mm-hmm.
whose diameter times the golden ratio, what comes out of it is a golden rectangle, right?
Mm-hmm. Yep.
So if I had that graphically, you would see a golden rectangle coming out of the diameter of the circle.
Right.
So 119 times 74 equals this number again. So I'll have the same number here, except I'm going to divide it by 1.618 and see what happens. Of course, I don't know what's going to happen because I haven't done this. Um, it's going to be a larger number. Um,
Mm-hmm.
so divided by 1.618. There. No, it didn't copy the number.
Yep. Okay.
Hang on a second. I got to copy this number. So now what you have to do is understand that why using half of phi produces a number very close to pi r squared. But the argument that I have for pi r squared, here, let me show you this. This is going to be a trick of the
Mm-hmm.
hand in the eye. I'm going to show you this. It's really funny, actually. See if you can. This is a hard one to figure out.
Could it suggest that the the traditional value for pi 3.141 is actually deficient because we're actually getting larger answers here that it could suggest, according to my view, that there's a different value, there's a true value for pi based on the golden ratio. So is there a connection that pi must be based on the golden ratio? Is that because the value I have for pi is 3.
That's where we're starting to go because you're right. Because the traditional method is pi r squared. In Egyptian pi is 22 divided by 7. And what we know as pi today, which is an ever, just like Fibonacci's sequence of numbers in the golden ratio, they don't ever end. They don't ever end.
Yep.
So of course, the bigger a circle gets, the harder it is to resolve perfectly. And
Mm,
again, if you do it like I did with square paper, so watch this. So look at this. Okay, so let's say this string, okay, in all spatial dimensions is the same length from the base of the string to the top, right?
right. Yep.
On side A and side B. But as soon as I make a circle out of the string, watch what happens.
Yep.
Now, if I take the diameter or the radius from the center of the string to the inner part of the string and the outer part of the string, pi r squared is going to give me two different numbers. But
Mm.
according to the string, this piece of cord, it's the same distance, right?
Yep. That makes sense.
So if
Yeah.
I take pi, let's just do pi, forget pi r squared. The diameter of this circle, it has an inner diameter and an outer diameter. The diameter times pi is supposed to give me the circumference, right?
Hmm.
But the circumference on all sides is the same number.
It's a
Doesn't
contradiction.
matter.
Yeah.
It's a contradiction. So the problem is, as soon as I make a circle out of it,
Mm.
and I have not stretched the string. In fact, the bigger my circle is, there'll be less and less stretching of my rope or my string or my cord.
Hmm.
But the diameter times pi now has an inner and outer dimension I've created in space time by making a circle out of something that's the same length on all sides. This is
Right.
the problem with number.
Hmm.
And this is one of the things Archimedes got into is pure volume is really what you're looking for if you're looking to define the volume of a sphere. So I decided to do an Archimedes test. And
Okay.
with an Archimedes test, I have one of my pyramids around here. What I did was I got a tank of water,
Right.
and this only works with a pyramid whose slope angle is Great Pyramid angle. And last week we demonstrated that using a golden rectangle,
This one here. I
right,
did the
you
calculation.
get Great Pyramid angle.
Yeah.
Now,
I ended up 50
what
degrees. I got under 51, but it's very close to 51 degrees. I did the tangent, the arctan of that angle. I did the arctan of that angle and got 50. I do it the old school way. I'm still by hand, but what did I get? 50 degrees point 026.
okay.
Yeah. Anyway, it's pretty good.
So
For me,
I
it's
got just
over.
under 52 degrees. Again,
Okay.
your physical rectangle, when I do it with a protractor.
Okay.
So when I submerge a pyramid solid in an Archimedean water tank, I displace a volume of water the same amount as a sphere whose diameter is the height of the Great Pyramid.
Beautiful. So that's
I
pretty much
displace the same amount of water. So the volume is far more accurate than the numbers, is what I'm saying, right? And that's how in the Archimedes Codex, let me show you when it was found. The Archimedes Codex was discovered. Um, Archimedes Codex. Let me see if there's any Wikipedia. Actually, here's what it looks like. So this is where the math gets really tricky because see, this is what happened is Archimedes's codices were printed over in another book that was discovered at a Christie's auction. I actually read all of this.
yes.
And so they had to pull the data out behind the book that was printed on top of Archimedes' codices.
Mm-hmm.
And this is what the math, when you read all this, that Archimedes gets into is exactly what I'm talking about,
Yeah.
is looking, how do you, what you're really looking for are not numbers.
Mm-hmm.
You're looking for a way to define the volume because in a way, a flat circle, that's another problem.
Mm-hmm.
The second I draw a line on a piece of paper,
Yep.
the carbon that I drew or the ink I've raised, it's no longer a two, there's no such thing as a two-dimensional object.
Mm.
There just isn't.
Yeah.
In nature, it's fictional. It's in the head.
Yeah.
And the head is trying to quantify what it's observing. And one of the reasons, this is another reason why really good physicists reject pi r squared. They said it doesn't exist.
Yeah.
And it doesn't exist for a lot of reasons because as soon as you create a number, you've created space by creating a number. And you create a number system, it can appear to resolve something visually because the eye is not trained. But
Right.
when you get down to really fine levels, you'll find that what Archimedes was doing is it's I love the story of the death of Archimedes because Archimedes is working on his greatest discovery,
Yeah.
and some Roman centurions have come to kill him and behead him.
That's
And
right.
they've got their swords up, and he's an old guy, and he's saying, "Just stop! I just need a few more minutes." And he's working on this formula, and they're about to kill him. I don't know why they're killing him, but just like Socrates was poisoned, they behead him, and
Mm.
he's not able to complete his final work. So when you go you take the time to go through the Archimedes lessons and the codices, you'll start to come to this conundrum,
Mm.
and realize that
Mm.
the the answer you're looking for
Mm.
is really, I guess, in a way, water. Of course, now water is going to change depending on its temperature, right? So
Mm-hmm.
when it's cold, it's going to contract. So you're going to have to pick like a moment in time in a temperature. This is how perfect you have to get to understand Archimedes. So if you're really looking, and I've wanted to do this. I mean, I would need a research grant to do this because when you have a small form, a solid pyramid, I used a crystal pyramid, I used a sphere who's the same height as that pyramid, and they both displace the same volume of water. And yes, I can mathematically calculate the cubic volume of the pyramid,
Mm.
but to calculate the cubic volume of the sphere, you can't really do it mathematically. You can only do it in milliliter units of volume of a liquid, and that's what Archimedes discovered. and
Right.
and you go through this in the codices that in the way the more numbers you add. So let's say I have the more units, so I have millions of a meter, and a billions of a meter is a nanometer, right?
Yeah.
So the more units you put in, you're now taking up space with numbers, and those numbers have to be removed if you want to know the truth.
Yeah.
And that's what I think Archimedes was working on, in the end.
So ultimately, this old expression, someone who's called crazy in the about a couple of hundred years ago, someone who was called crazy, they called him a circle squarer because so many people hundreds of years ago were trying to make the equation of the circle square equal. In fact, I've got here in 1775, the Paris Academy, the French Academy of Mathematics, they refused to even inspect any more theories that the square and the circle could possibly equal. So they deleted all references to any mathematics based on the squaring of the circle. So the reason why we're having this discussion now is that if you went to any university today, we're considered mathematical nuts because we're trying to make the mystical quadrature of the circle equal. So there's been a big pause in this research. So I mean, I really hope you get this grant because I think it's a place where the celestial and the terrestrial, the heaven and the earth meet at that critical union where these two apparent opposite geometries have a resonance. It could be like this particle wavicle theory where somehow they're both. We need the square and the circle to understand the universe in some way.
Well, I think it's one of the most fascinating arguments. Let me put up another document. So when you understand that the three pyramids at Giza, as Arabs pronounce it, and Giza, as local
I
Egyptian
like
Arabs
that.
pronounce it,
Jesus, beautiful name.
the the three pyramids all have slightly different angles, which means the rectangle base to form the angle of each pyramid is using slight variations of phi.
Right.
Now, remember, phi is not absolute. So you have to wonder why the smallest pyramid, which is Menkaur's pyramid, is 51.340 degrees, 278. Khafre's pyramid is 51.84, and Khufu's is 51.853972. I mean, that's when you convert 51 degrees, 51 minutes, and 14.3 seconds. So yes, as you pointed out just moments ago, your rectangle is going to vary that when you fold the corners in
Yep.
to produce the variances in these angles. And the variances of these angles, and this is where I go really deep into phi and the pyramid complex in Giza and what's called the harmony of the order, which is the harmony of the order of the entire solar system and a hyperdimensional solar system, is why each pyramid over time has a different angle, because what it's tracking in the heavens above is sitting at an angle that is is changing slightly over time, right?
Hmm.
So if you did a study on this, and also last week we pointed out the dimensions of the human skull and other mammalian species done at Johns Hopkins University, which I pointed out,
Yep.
you have variances of phi to different skulls of different human beings in different mammalian species that range between 1 to 1.5758 and 1 to 1.6 to 1.63, etc. So that means if you were to convert that back into a rectangle and check your angles on your corners, they're going to have varying angles,
Right.
right? That will range between 51 degrees and 52 degrees, but they're somewhere in there, but they're not exact. And in fact, if you go through Fibonacci sequence and you make a series of rectangles and check your corners on the progression, like a 3-5 ratio in Fibonacci produces a 1 to 1.666666.
That's right.
And you should see what I do with that in the
Okay.
harmony of the order. So when you're ready, I'd love to, walk you through the harmony of the order calculations from the
Well,
Giza Plateau
well, we're coming to an end
and
of.
see what you think of that.
Well, I think we've done about 45 minutes, which is great. So, if we were to do a third lecture or rant, would you like to talk more about the relationship with 591 and the golden ratio in the heavens?
Yeah.
I'd love to.
And the heavens and what's called the harmony of the order, which is how the heavens imprint upon the earth itself.
Can I
And again, your
close?
your golden ratio
Yep.
is a progression, it's a movement.
Okay.
And I think these three pyramids, right? That angle is so sacred. It's more sacred than anybody could possibly imagine, than
Really?
Tompkins and Peter Lemessurier, who demonstrated some profundities to the meaning of why the Egyptian pyramid on the inside, the ascending and descending passages
Right.
are 26,
Are they both the same
26.3
angle?
degrees. That's going to be a clue to the heavens.
Right. Are they both the same angle, the ascending and the descending? Are they both 26 degrees?
Yeah, they're pretty much the same. I mean, if you, depending on how accurately it's measured, there might be a slight variance,
Right.
but that is key to what I'll go into next time.
Well, until next time, Dave,
Okay,
thank you very much. Bye.
thank you, Jane.
Bye.